Welcome everybody to the event New Perspectives on K and L Theory. This is the first lecture of series given by Markus Land about L theory of rings via higher categories. Markus is an expert on that area. He's currently in Copenhagen and he's going to give 3 talks on that, which I mean you might follow through Zoom, but also through YouTube. So this whole event will be uploaded on YouTube, so that you can actually watch the talk. There's the companion lecture series by Jonathan Harpas. First of his talks is already on YouTube, so make sure you go to the YouTube channel of Mathematics Münster, which is linked through the homepage, and watch Jonathan's talks as well. And there's one special thing about this lecture, this whole event, namely we've put up a forum. This is a mass overflow style forum. And on this forum, we will have questions and discussions about these talks. So the idea is to have the answers to the talks available also for people watching these talks later on YouTube. So if you have a question after the talk, Achim just posted the link. You will also find the link in the description below in YouTube. And Markus will also have some exercises questions in his lecture, which we also already posted on this forum. So whoever answers them first will get the check for the right answer. And if we don't have a correct answer to any of these questions, we will resolve it in 2 or 3 days and write a sort of standard answer for the question. Okay, after this introduction, it's a pleasure to hand over to Markus for the first talk on L theory of rings via higher categories.
Great, yeah. Thank you, Thomas and Arthur, for organizing the event, and in particular for inviting me to give this series of lectures. So I want to start sort of basic and remind you, if you've seen the video of Jonathan's, or tell you about the setup in which I want to sort of have these lectures been placed in, which is just saying that we fix a ring. R need not be commutative, can be any good old ring, but for the moment it's really a discrete ring, not a ring spectrum, nothing homotopical fancy going on. And M is what we call an invertible module with involution over R. So that's a lot of words. Let me explain to you what those are. So in other words, firstly, M, so that's the first part, M is a module over R tensor over R. So because M is just a discrete module, you can either just take it as an ordinary module over R tensor over the R, or you may also view it as a module over the derived tensor product here. Oh, you still, it has happened. I'm so sorry. I have to stop the synchronization and make it happen again. It was just there a moment ago. All right, let's do this. Good. So you can view it either as a module over the derived tensor product or the underived tensor product. Both things would be just equivalent data. And we observe that this tensor product has a flip isomorphism, this CMOD2 action given by swapping the 2 factors. And what this module is supposed to come with, that's the datum of an involution, is just this map sigma, which is an isomorphism from R to, well, the same abelian group M, but viewed with the twisted R tensor R module structure. So concretely, that just means that we have an isomorphism which satisfies that sigma of something like R tensor S times X equals S tensor R times sigma of X. Okay, so that's just what it means to be an isomorphism to tau upper star of M, and then we require this to be an involution in the sense that it squares to the identity. Okay, so that would be the terms that M is a module with involution over R, and it being invertible says that, well, take either of the 2 factors in the first or the second factor and view M as an R module, and then you wish that M is finitely generated projective, and in addition that the map from R to the R linear endomorphisms of M is an isomorphism. So that's a general setup in which we want to deal with symmetric bilinear or quadratic forms or whatever, n-valued bilinear forms. So this is just an abstract definition. Examples are as follows. So the first example to think about is just if you have a commutative ring R and M an ordinary invertible module in the module category of R, right? It comes with a tensor product over R, that's a symmetrical module category, and we can ask that M be an invertible object in there. In other words, that there's another R module N such that M tensor over R, N is isomorphic to R. So these are called line bundles in algebraic geometry, or just rank 1 finitely generated projective modules. So, well, how do we get this data of an invertible module with involution? Well, we have to give it an R tensor R module structure. That's good because the ring is commutative. We can take the multiplication map and view this R module as an R tensor R module. And as an involution, we can just take any endomorphism of M as an R module, which has order 2. So the most canonical examples would be just plus minus the identity of M. And I encourage you to think for a moment that these data in fact satisfy all these assumptions that I wrote up here, in particular this point. Or if you're watching on YouTube later, this is a good point to click pause, check that this is all good and fine, and continue to watch. Okay, so the second example would be coming more if you have a background in, say, surgery theory. Or these are the kind of rings that appear in this world. So we say a ring is equipped with an anti-involution if there's a map iota, say from R op to R, which is an isomorphism. So just an iso from the opposite ring to itself, which also squares to the identity. And then we want to fix a unit, epsilon, say, which is central and satisfies this assumption that its inverse is given by iota applied to epsilon. And in this case, we can set M equals to R, right? So the module is just the ring itself. Well, of course, the ring is an R tensor, well, an R bimodule, which means it's an R tensor R op module. And then we can use the involution in one factor to obtain an isomorphism of R tensor R with R tensor R op. So in this situation, R is itself canonically an R tensor R module, and you define the involution sigma of R by epsilon times iota of R. Okay, and again, the typical candidates would be that epsilon is plus minus 1, and the typical rings where you find such anti-structures is a group ring, say over the integers, and then you can let iota be determined by mapping a group element mainly to its inverse, and then you're allowed to add a so-called orientation twist to that. So if you fix any group homomorphism W1 from G to plus minus 1, reminding ourselves of, if you have a manifold, then its first Stiefel-Whitney class is such a homomorphism. Then you can twist your this construction mapping G to G inverse by that orientation character. So these are typical examples of such rings equipped with a module with involution, which is in addition invertible. Good. So that is the setup that we want to describe. And what are the objects that we want to describe in terms of this setup? Those are what we would like to be. Right. Okay, so we need a couple of more definitions first. So if we have such a ring with an invertible module with involution, we would like to consider the category of projective R modules, or finitely generated projective R modules to be more precise, and observe that the association sending a P to its R linear maps from P to M, that in fact will be a duality equivalent from finitely generated projective modules to itself. Contravariant functor, so we have some op flying around. Okay, so let me explain briefly how is this even an R module, where you take one of the R tensor R module structures of M to form the R linear Hom, and you take the other one to give that R linear Hom an R module structure. And by the fact that we have this involution sigma on M, it actually doesn't matter in which order you do these two things. Right? So both of these will be again finitely generated projective. And well, then you check that this is again a finitely generated projective module. And if you do it twice, you will use, I suppose, this assumption here that R is isomorphic to the R linear endomorphisms of N to deduce that this is really an autoequivalence of finitely generated projectives. And of course, if R is just commutative and M is the canonical line bundle, just R with the trivial involution and everything, this is just the ordinary duality, in projective modules, homing into R. It's again a perfectly nice projective module. And this is just the general version of that situation. Okay, and now what we do, or what we consider, is the group of R tensor R linear homomorphism from P tensor over P to M. Okay, so that makes sense. P tensor P is an R tensor R module. M is by assumption an R tensor R module. So what remains is an abelian group, and we call that the abelian group of bilinear n-valued forms on P. Right? Any such gadget will of course be just a function, say B, from P tensor over P to n. And now we observe that this group of bilinear n-valued forms acquires a canonical C2 action. So where does the action come from? Well, on the one hand side, we can flip the two factors of P tensor P. That gives an action on the first term. Sigma is by definition an involution or an action on the n. And now you just have to believe me that everything is made in a way that conjugating these two actions in fact induces an action on this set of bilinear n-valued forms on P. And so what you can do is you can look at the orbit space of this action and the fixed point space of this action. So here's the space of orbits, or the set of orbits, group of orbits, and the group of fixed points. And we call them the n-valued quadratic forms and n-valued symmetric forms. Okay, so let me also tell you that there's a canonical symmetrization. I mean, if you're more familiar with this is a norm construction. So whenever you have the group C2 acting on any abelian group, then there's a canonical map from the orbits to the fixed points given by just summing up the action. And this is essentially given by sending something like maybe x in here goes to x plus sigma, or I mean tau of x. So we have to be a bit more careful which what the action is. So maybe let me just say t of x, where the t is the action. The C2 generator, say, is called t. And so that gives a map from n-valued quadratic forms to n-valued symmetric forms. And the image is also sometimes called, so the image of the symmetrization map is then n-valued even forms. So these have appeared in Jonathan's talk. If you've seen that, or I mean, if you will watch it afterwards, then you will recognize it. And okay, so the first exercise that I wanted to convince you to maybe think about is that you can describe the set of n-valued quadratic forms equivalently as follows. So first, it's given by a symmetric bilinear form, which is going to be the image under the symmetrization map. So you're supposed to be given a symmetric bilinear form, and then you need a function q from P to the C2 orbits on M, satisfying some compatibilities. Q of Rx is supposed to be something like R tensor R of Qx, and so on. Okay, so there are these three compatibilities that you need to check in order to recover the datum of a C2 orbit acting on this group of bilinear n-valued forms. So that's an instructive exercise to understand. And of course, this, I mean, mainly particularly this equation tells us that Q is really quadratic, right? I mean, it sort of pulls out an R in this X factor to an R tensor R multiplication. So this is really a quadratic function. And then the other terms are just saying that, well, the symmetrization of that quadratic function is in fact symmetric bilinear. Okay, so that's a good exercise to try to work out, to familiarize yourself with this construction if you don't already know it. Okay, so then
maybe, sorry, Markus, to interrupt, but maybe at this point we should say again, this will be one of the exercises that you'll find in the forum. So please, I challenge everyone to go there and write an answer, or if you can't figure it out, you'll find a good answer at least in 2 days from now. Maybe earlier if some participant gives a good answer.
Right, yes, Thomas, thanks. So again, all exercises I've listed here appear on the forum. Feel free to put in corrections if something's wrong, or solutions if everything's right. Okay, good. So we will say that an n-valued symmetric form is unimodular, or sometimes it's also called non-degenerate, if the associated map from P to this M dual of P is an isomorphism. So recall that an n-valued symmetric form is still a function from P tensor P to M. And of course that is, I mean, by an adjunction equivalently described in terms of a map from P to hom R P to M, which was by definition the M dual of P. Okay, so any such symmetric bilinear form gives rise to such a function, and then you say the form is unimodular if this function is an isomorphism. And so a canonical example that you can at least write down, so at least, I mean, you can always guarantee that there are some unimodular forms around, namely is the hyperbolic form. So what you do is you start out with a good old projective module, and you consider the module P plus dual MP, right? I mean, in particular, in order to have a unimodular form, you need to have a module which is self-dual. So the easiest way of finding self-dual modules is just take the module, add its dual, then it's been self-dual. And now you have to come up with a clever form. I just wrote down an evaluation form, and again, it's the content of exercise 2 to show that this hyperbolic form is actually canonically a quadratic form, and I will let you think about all the details of writing this out. But I mean, essentially, the function is going to be given by this evaluation map from P plus the dual of P to M itself. Okay, very good. Slightly more set of definitions that we will need in this ordinary algebra, just to be on the same page on what concerns these basics of symmetric bilinear forms, is that a symmetric bilinear form is P, say, B on a projective module P is called metabolic if there exists a Lagrangian. Okay, so a Lagrangian is what's called a maximally large isotropic subspace. So what is that? It just firstly means that L is a submodule of P, and you just demand it to be finitely generated projective itself. And it's supposed to be such that the sequence, when you map L to P via this inclusion, now you pick your unimodular form B, which gives you an isomorphism to the M dual of P, and now you can dualize this inclusion from L to P, right? So if you take the inclusion from L to P, you dualize, you get a map from the dual of P to the dual of L, and you require that this sequence is short exact. Which roughly speaking says that P splits up because L is also a projective. P will split up into L and the dual of L, and you will have a form saying that B on L vanishes. Right? Okay. So that means, in addition, B restricted to L 0, and it's maximally large with that property. And I think I should add a symmetric unimodular form, right? So that we have this isomorphism. Good. Now, if your form happened to be quadratic and L is a Lagrangian for its underlying symmetric bilinear form, it's not necessarily a Lagrangian in the quadratic sense. So the correct notion, of course, that we want to add is that in addition, Q also vanishes on L. Not only the bilinear function vanishes on L, but also the quadratic function vanishes on L. And again, I would suggest that you try to find out that this assumption is not always automatic. Right? In any case, another exercise about these basics is that if you have a quadratic form on P, which admits a Lagrangian, a quadratic Lagrangian in the sense that I've described, then in fact, this form is isomorphic to a hyperbolic form. So you can give a purely algebraic proof of this, but if you don't want to do that, there's a hint. You can wait until the end of my second lecture, hopefully, and in the second lecture, or at least at some point, you will learn a different way of how one can prove such a result. Not, being of the kind writing down isomorphisms of modules in terms of bases or something. Good. But a different property is that you should also convince yourself that not every metabolic symmetric form, as we've defined it here, is hyperbolic. Right? So that is also not supposed to be the case. So this is a feature of quadratic forms, that if they admit a Lagrangian, then they're hyperbolic. In general, forms, symmetric forms which admit a Lagrangian are only, they admit a Lagrangian need not be hyperbolic. Okay, good. So let's continue with definition. Oops. So what we want to define is Witt groups of such symmetric forms. They've appeared in Jonathan's talk, as a recipient of a map from the Grothendieck-Witt group of symmetric or quadratic forms. So these Witt groups are supposed to be easier and help in the calculation of higher Grothendieck-Witt groups. So my lecture series will focus on these Witt group theoretic ideas or L-theoretic ideas. So if we fix R and N as before, a ring and a module, invertible module with involution over R, we can consider the isomorphism classes of unimodular n-valued symmetric forms. That's certainly a set. And with the direct sum or orthogonal sum of such forms, this becomes an abelian monoid. Okay, so this object is an abelian monoid, and you can just divide out the submonoid generated by metabolic forms, so all forms that admit a Lagrangian. Let me warn you that the way you define quotients in monoids is, I mean, it does not mean that the subgroup generated by metabolic forms is precisely the kernel. Okay, we'll come back to this, but it can happen that that you have an object where you add another object and then it becomes metabolic, but before it hadn't been metabolic, right? So these things can happen. So in monoids, we have to be careful with kernels. And likewise, we can look at the quadratic Witt group, which is just isomorphism classes of unimodular n-valued quadratic forms. This is an abelian monoid, and we can divide out all such forms which admit a quadratic, or which are quadratically metabolic, or in other words, which are hyperbolic if you solve exercise 3. And again, a good exercise to do and to write a solution in the forum is that, well, these quotients, which are defined in terms of monoids, are in fact abelian groups. Not only monoids, and in addition show that the symmetrization map induces a group homomorphism from the quadratic Witt group to the symmetric Witt. Okay, so that's not so complicated. And the main idea is to show that, well, in order to see that these things are groups, you just have to show that inverses exist. And for this, you need to have a candidate for the inverse, and here's the candidate for the inverse. So try to show that P comma minus B is in fact an inverse in this quotient monoid 2P comma B, and hence every element has an inverse, and thus this quotient monoid is in fact a group. Okay, good. So that's the definition of the Witt group. Okay, so a proposition I'd like to prove is if you have a field, then the symmetric Witt group of K, okay, I should have also maybe explained this notation. So if R is itself commutative and M is just R and sigma is the identity or minus the identity, then I will write just the Witt group S or W minus S or WQ or W minus Q for these, to save space. And so if we take a field, then the symmetric Witt group of K is generated by forms that I write Langle U wrangle. So which is just the underlying modulus K, and the bilinear form is given by sending X tensor Y to U times X times Y for a unit U in K. Okay. Good. So if you watch this live, then you will have to pull through the proof with me. But if you watch this online, and everything had already happened, I invite you to click pause, prove this yourself, and then just skip over the proof. Okay, so how do I wish to prove this? The first thing is that if you take a symmetric bilinear form over your field K, let's assume that there exists an element X in V such that Bxx is some non-zero unit, some non-zero element and hence a unit. So if that's the case, then you can just define V prime as the orthogonal complement of X. So by that, I just mean the kernel of the function B of X comma blank, which is from V to K. Because this is a unimodular form, V prime will have dimension 1 less, and you can restrict B prime to V prime, and then you can check that VB actually becomes isomorphic to this form Langle U wrangle plus V prime comma V prime. So inductively, what we get is that we can write any form over a field as a direct sum of one-dimensional forms of this kind, plus a form which is bilinear and in addition satisfies V prime of X comma X is 0 for all X, right? Because if there were another element, then we could continue, right? Okay. Now, here are two exercises that you, again, can think about. The first is that, maybe this was the wrong direction, but if you assume now that the characteristic of K is not 2, then you should convince yourself that any such form as of this kind, which is symmetric bilinear, and in addition satisfies this, which is usually called, it's also skew symmetric, any such form forces W in this case to be 0. Okay, so this is a purely characteristic 2 phenomenon, and outside characteristic 2, any form is in fact itself the direct sum of one-dimensional forms. So in characteristic 2, this is not necessarily the case. And as another exercise, this here, exercise 5, you can calculate outside of characteristic 2 some of them. Okay, so what do we do with this remaining W, B prime? Well, we essentially only need to show that it's representative, or it represents a 0 element in the Witt group, and then we're good. Because, yeah. Okay, so this is precisely what we have here to finish the proof. It suffices to show that this form is 0 in the Witt group, and then obviously the rest tells us how to generate any form in the symmetric Witt group. And for this, this is also very easy. So suppose W is not itself 0, then you can find an element such that X pairs with Y to 1. We can do this because B is a unimodular form. So yeah, B of X comma blank is surjective, and hence we can find such a Y. And then again, you do the same as before. You define W bar as the orthogonal complement of the subvector space spanned by X and Y. You define B prime bar as the restriction to W bar. And now you observe that X itself spans a Lagrangian inside XY. Okay? So I will let you check that. But this tells us that in the Witt group, W, B prime is in fact equal to W bar, B prime bar. But now this vector space has strictly smaller dimension, and so we can deduct. Okay. Good, great. So we've proven a lemma, that's good. And so what we want to do now is take this.
Can I ask you a question?
Yes.
Hi, it's Alden. How's it going? Yeah. So how do you find this X at the beginning? Like, assume there exists an X such that Bxx equals to U, which is non-zero. How do you just produce this X?
Well, I mean, I say assume it exists, and if not, then you're here. I mean, then if it doesn't exist, then you're just in the case where you have a skew symmetric and symmetric form. That's just 0 in the Witt group.
Thank you.
You're welcome. Okay, so what I want to do now is I want to switch the situation a bit and connect to the title and theme of these lectures, which says we want to do L theory and Witt theory with higher categories. So now we want to go away from projective modules, an ordinary duality on projective modules, and defining just an ordinary Witt group in these terms. Rather, we want to take a step back and define something that is called a Poincare infinity category, explain what it means to have a unimodular form in this context, and then define an analog of Witt groups, so-called L-groups for these Poincare infinity categories. And then ideally we want to connect back and explain how to calculate these more general L-theoretic invariants of Poincare infinity categories purely in terms of Witt group information of, say, fields and Dedekind rings. This is what sort of the very goal of this lecture series is. We want to calculate L groups of certain types of number rings through only Witt theoretic and sort of maybe K theoretic information. But to set the stage, what we need to construct, or understand, is what is a Poincare infinity category. So that is a tuple C, coppa, where C, what is it? So C is a small stable infinity category. So the good examples would be finite spectra, the derived category of perfect modules over a ring or a ring spectrum, maybe the derived category of perfect complexes over a QCQS scheme. There are probably more examples around that you could care about. Of course, in the algebraic context, what we will be interested in is these derived categories of perfect complexes over an ordinary discrete ring. So that's what C is, a small stable infinity category. And now kappa is what we call a Poincare structure on the stable infinity category. And it's just a contravariant functor with values in spectra, which is reduced and too excisive in the sense of Wood-Wheeler calculus. So this is supposed to also have appeared in Jonathan's talk, but let me tell you, so reduced just means that kappa sends 0 to 0. And too excisive means that it's not quite a linear functor, but you can explain you can give a formula for the failure of this function being linear. And more precisely, this is given as follows. So you can construct what's called the cross effect B kappa of xy, which is just the cofiber of kappa of x plus kappa of y sitting inside kappa of x plus y. So by functoriality, there is such a map. Maybe you can also use that this functor kappa is reduced. And the condition is that this function is symmetric bilinear in the variables x and y. So it's linear in both x and y, and it's symmetric in addition. And so that's not quite what a Poincare infinity category is. In addition, we require a certain non-degeneracy condition. And that just says that this symmetric cross effect P kappa xy is supposed to be of the form, well, it's the mapping spectrum in C from x to dual kappa of y for some duality equivalence P kappa from C up to C. Okay, so you can observe that, well, this functor is also contravariant in x, contravariant in, and is, well, the assumption is that B kappa of xy is of this kind. And whenever this is the case, then in fact C equipped with this duality will be a coherent this is going to be a coherent duality in the sense that this pair is in fact going to be a homotopy fixed point for the action on cut infinity x, so stable infinity categories, sending a category to its opposite. But nevertheless, this is really a pointwise condition by the assumption that already B is assumed to be symmetric bilinear. So really the symmetry condition in this functor gives this HC2 fixed point on the duality. Okay, so this is what a Poincare infinity category consists of. It's just a stable infinity category plus some Poincare structure, which allows us to extract a duality equivalence.
Can I ask another question? Sorry.
Please.
So if you have a reduced to excessive functor, then the cross effects determines that reduced to excessive functor, right?
No, there is also a linear. No, there is a linear approximation. And
yes.
That together. I'll come to that in a moment. But good,
okay, so it's more data than just the cross effects, right? Thank you.
That's right. It's more data. This is something. Yes, I'll come to it in a moment. Good. Okay, so I want to not dwell too much on general examples, but more the examples that we care about for this series of lectures. So again, we pick a ring and an invertible module with involution M as in the beginning, and then say a Poincare structure kappa on dp R, so the derived category of perfect complexes on R. Oops. So this is the perfect complexes on R. So perfect chain complexes just means they're represented by finite chain complexes where each term is finitely generated projected. And it's called compatible. Such a Poincare structure will be called compatible with M, or also sometimes N compatible, if the duality that is associated to this kappa is of the form just map R blank comma M, right? Which is just the same duality we've had earlier on the level of projective modules. But of course, this formula of mapping any perfect complex into M will still it's still a formula, and you can convince yourself that this functor gives rise to a canonical equivalence on the level of these derived categories. And being compatible with this just means that the abstract duality we obtain from the definition of the Poincare structure is supposed to coincide with that. It also turns out that whenever you have any Poincare structure on this derived category, then from it you will be able to extract such an N. This is essentially how we also came up with the definition of these modules with involution. They are just the things that that determine such dualities. Okay, so concretely, this just means that the cross effect B kappa that we've written down here is of the form x comma y maps to the mapping spectrum of R tensor R from x comma y to n. Okay, so that's just the formula for the cross effect for a functor which is compatible with this module of involution. Okay, good. So then we can move over, and I can come to the question that was raised by Eldon just a moment ago. So the fact that we wish to make use of is that reduced N2 excisive functors on any stable infinity category are classified by two pieces, may say three pieces of data. On the one hand side, there are symmetric cross effect B copper that I've just written down in terms of the cofiber of some map of copper x plus copper y to copper x plus y. And their excisive approximation, right? Any functor, which is not linear in general, can be approximated by an excisive functor from the right, called the linear approximation in the terminology of Kuhn calculus, which I want to write as L copper. And in fact, there is one more piece of data you need, namely copper of x will be, you will be able to reconstruct it as follows. So by the compatibility condition, there will be a map from copper of x to this object, map of R tensor R, x tensor x, m to the upper HC2. This is really by definition of M compatibility. So maybe I should add exercise. So that's not on the sheet, construct this map. It's a very canonical map that's part of the data. It's essentially built out of the diagonal. I'm confused in any case. So then there's a second piece of data that we can write down, namely the linear approximation. And as I've said, any functor can be approximated from the right by a linear functor. So we have this morphism, which is this excisive approximation. And then these two terms have to be glued together in a correct way. And the way one does this is to pass from the homotopy C2 orbit construction to a Tate construction. This is sort of the spectral analog of just ordinary Tate cohomology. So this is, to be more precise, this Tate construction is given by the cofiber of the norm map. And the norm map is, again, a homotopical version of the symmetrization map that we've seen earlier. So there's a symmetrization map going from homotopy orbits to homotopy fixed points. Its cofiber is the Tate construction and gives rise to this fiber sequence. Okay, and now there's a classification of linear and excisive functors, which tells us that, well, A, you have to show that this functor is in fact linear in X. That's something one has to prove, but which one can prove. So this functor, then by the classification of linear or excisive functors on the derived category to spectra, will be equivalent to a functor of the kind just sending x to the mapping spectrum over R from x to m to the Tate C2. But we have to be very careful what this means. So in particular, in order for this formula to make sense, m to the Tate C2 has to have the structure of an R module. And let me just remind you that sigma is this is an action on M, so sigma acts on M, so this is a C2 action, with respect to which we can take this Tate construction. And then you have to remember that this sigma function was equivariant with respect to the flip action on R tensor R. So it turns out that from some monoidality constructions on the Tate construction, M to the Tate C2 will be canonically in R tensor R to the Tate C2 module, because M was a module over R tensor R and the actions were compatible. And then there's this bit of homotopy theory magic appearing, saying that there is this canonical Tate diagonal map, which is a ring map from R to the Tate C2 construction on R tensor R. So that makes M to the Tate C2 an R module. And it turns out that this functor here is equivalent to the mapping spectrum functor on the right-hand side. So all of this uses quite some machinery, which you do not need to understand in order to follow the rest of the talks. I just wanted to explain to you how, in general, quadratic or these Poincare structures arise from individual pieces of data. One of the pieces of data is this module with involution M, giving rise to these lower terms. And then another piece of data was this linear approximation, which by a similar analysis is given just by the mapping spectrum from R over R from X to some other module N. Any linear contrariant functor is of this shape for some R module N. And the statement is that any such reduced and two excisive functor can be reproduced from this object M and this object N by gluing together these two terms along a map of this kind, which is induced by a map from N to the Tate C2. So let me summarize this in the following diagram. So consequently, any compatible Poincare structure is described by an R module N, right? This is the one that gives rise to this linear approximation, and an R linear map from N to the Tate C2, giving rise to this map. And then we can take the pullback, define that as kappa of X, and well, you will see that this functor here is clearly, so visibly symmetric and two excisive. So this is sort of a quadratic functor. And well, these both are linear, hence in particular reduced and two excisive, and then such functors are stable under the formation of pullbacks. So kappa of X will automatically be of that kind. So the canonical examples you should keep in mind about this are the following stupid points. So N can be 0, and what you obtain is something that I won't call. So this is just this right most left-hand term given by taking the homotopy C2 orbits on X tensor X mapping to N. Well, why is that? Well, imagine here is a 0, right? If N is 0, then by definition this term is just the fiber of this map, and hence it's the orbits by construction. So the other extreme, of course, we can do is to say that N is equal to N to the Tate C2, and this gluing map is the identity. This will say that this map is an equivalence, and hence by pullback property, this left-hand map is also an equivalence. So in that case, kappa of X is what I want to call kappa symmetric M of X, because yeah, it reminds us of symmetric forms, these C2 orbits, C2 fixed points. Okay, but here's another canonical set of examples you can take. Namely, you can let N be any truncation or connective cover that are a connective cover of M to the Tate C2, which comes with a canonical map to M to the Tate C2, the universal map in this connective cover map. And this will give rise to quadratic functors I want to denote by kappa of M greater or equals to M, because it takes these connective covers. They will appear in a moment also. But other examples are also, for instance, if you take a commutative ring, N equals to R, sigma the identity, and you can also take N equals to R. So this term here will be just given by mapping X to R, really just taking the R dual. And then you will have to construct a map from R to the Tate C2. And for that, you take this Tate diagonal, and then you compose with the multiplication map applying Tate C2 to that. So this composite is usually known as an E-infinity Frobenius for a commutative ring. That's some interesting map that exists. And from it, you can also construct a Poincare structure that we call the Tate Frobenius Poincare structure. And because it appears in an exercise, here's another construction you can do. If you have a commutative ring, again, R, N equals to R, sigma the identity, then I want to construct a sort of 1/2 connective R to the Tate C2, which is you take the connective cover of the Tate construction. So it has at most a pi 0, but no negative homotopy groups. And now you calculate that its pi 0 is R modulo 2. And then you just take the pullback over R modulo 2 with R. So effectively what happens is you just replace the pi 0, which is on R mod 2 by R itself, and all higher homotopy groups remain the same. This is a general construction one can do. And we will call that construction kappa RB. As, in some exercise, we'll see that it has a relation to the Burnside ring for C2. For the, So that's also a construction you can do. And the exercise that I really encourage you to do, or I mean to click pause now and do it, or whenever you get the chance, is to show the following. Namely, that if you take this kappa greater equals to 0, or kappa greater equals to 2, or for that matter also kappa greater equals to 1, and you evaluate it on a finally generated projective R module, then what comes out is a spectrum which has a single homotopy group in degree 0, and in that degree it's given by the group of m-valued symmetric forms in this case, or the group of m-valued quadratic forms in the second case. And now in Jonathan's lecture we've learned that Poincare structures, or in general these two excisive functors, are determined by their effect on finally generated projectives. And so you will see that what I denoted by kappa greater equals to 0, in fact, is what Jonathan called genuine symmetric or genuine quadratic Poincare structures. So that is really just to say that the sort of the set or the space of forms that kappa associates to a projective module is not a homotopical version of symmetric or quadratic forms. It's really just the set of quadratic forms or symmetric forms sitting in degree 0 and nothing homotopical fancy around. Sort of the actual symmetric and actual quadratic forms appearing. And as I said, in this case with the kappa Burnside ring of Z, it's a fun exercise to convince yourself that if you evaluate kappa B of the integers at the integers itself, you obtain the Burnside ring of C2. Okay, so those are examples that one can consider. And next I want to give a definition, namely the space of forms associated to an infinity. So the space of forms, C kappa, is, okay, let me give an abstract definition. It's the groupoid core of some broken deconstruction of the functor, which functor is it? It's omega infinity kappa, which is a functor from C op to spaces. Right, and any such functor has a group deconstruction. It's some right vibration over C or something, some infinity category lying over C op, and you can take its groupoid core. Concretely, this really amounts to saying that points in the space consist of pairs x comma q, where x is in C, an object, and q is a point in the infinite loop space associated with kappa of x. Okay, so that's just what this is, but okay, I just want to convince you that there is directly a space of such forms around. The points you can imagine as such pairs, an object in C and a point in omega infinity of q of x. And such a pair is called a Poincare object and not a general form object if an associated map from x to the kappa dual of x is an equivalence. And so, so let me here say, so exercise prime, construct this map. But I can tell you that if you've solved this exercise, then it will not be complicated to also solve this. Okay, so there's a very canonical map you can construct from x to the kappa dual of x, and that map, if that map is an equivalence, then you call this object a Poincare object. This is sort of our higher categorical analog of a unimodular form, and not just any Gaussian form. Right? You have some non-degeneracy condition, saying that the map to the dual is an equivalence. And then we define the space of Poincare objects of CQ inside the space of all forms to be all the connected components on objects which are Poincare. It's just a collection of path components indexed by all of them which satisfy this Poincare condition. Okay, so the next definition that we need to make in order to get closer to defining something like a Witt group or an L group in this more general context is going to be the notion of a Lagrangian. Right? We've explained what is a form, what is a unimodular form, but we also need to say what is a Lagrangian of such forms. And a Lagrangian consists, well, first it has to be a Lagrangian in something, so it's a Poincare object xq. And then the datum of a Lagrangian is sort of a pair L comma eta, where L in fact comes with a map to X, say call it F, and eta is a null homotopy of the restriction of our form Q along F. So recall that there is a map, so omega infinity Q of X, and then there is omega infinity kappa of F. Right, it's a contravariant functor, So we can take our point Q and pull it back along this functoriality and obtain some point in L. And that point we wish to be connected to 0 in the space omega infinity kappa of L. And you want to have it in a way that makes the following diagram, namely you go from L to X. Again, you choose your, you take this Q sharp, which is an equivalence to the kappa dual, and then you dualize the map from L to X. So the condition that eta comes, or eta is a null homotopy of this restriction, will tell us that this diagram canonically commutes. So this composite from L to X to dual L, in fact, is canonically null homotopic. So this is in fact a filled diagram in our infinity category, and the question that we raise is that it be a pullback. So if that is the case, then we call this pair L and eta a Lagrangian inside X, Q. And then the definition of an L group is now the analog of the Witt group we had before, namely the zeroth L group consists of equivalence classes of Poincare objects in C, kappa. Again, under direct sum, these form an abelian monoid. And then we define out metabolic objects, i.e. objects which admit a Lagrangian, just as before. And also, just as before, the exercises are to show that, well, this is again a group, and the same hint as before works. You just want to show that this quotient monoid in fact is a group, so you just show that inverses exist and they satisfy the same formula as before. And secondly, here's something the relation x comma q is in relation to x prime comma q prime if and only if the direct sum x comma x prime and q plus minus q prime is a metabolic object. So admits a Lagrangian. You can just say x and x prime are related. If this is the case, then this is a congruence relation on the set of Poincare objects, i.e. it's an equivalence relation which is compatible with the direct sum. And yeah, so from that it is you can show that an object in a Poincare object is 0 in the L group if and only if it actually admits a Lagrangian, not only maybe up to adding other terms, which was not the case in the Poincare or in the situation of the Witt group we had before. And finally, use this to show that the L0 group that I've just defined is isomorphic to the L group defined in Jonathan's lecture via cobordism groups. Okay, so let me try to finish today's lecture.
Sorry, can I ask a question about that last theorem?
Yes.
Does this indicate some sort of universal property of L theory that we should expect? What's known about universal properties of?
Well, I mean, L theory will, at the end of the day, have a universal property, and it will be the universal object which sees broadened objects as equal. And so, in some sense, the answer is yes, but no.
Okay, thanks. Yeah, thanks.
Yeah, sorry. So we most likely might come to the universal property of L theory in either the end of Jonathan's lectures, or if not, then we can discuss it over the coffee afterwards. Okay, so I want to finish today's lectures with the following goal, namely to define an L theory space associated to C and kappa and describe its higher homotopy groups, or the higher L groups. So in Jonathan's lecture, if you've seen it, the L groups were just defined uniformly. In some sense, you just do some construction and out comes a group. And we will recover this notion, but I sort of want to take a step back and say, let's define a space and see if we can analyze what the homotopy groups of this space are. And the observation I want to make is the following, namely that, so we've just talked a little bit about this relation x and x prime being related if and only if there is a cobordism between them. So the observation is that the sum admitting a Lagrangian can be reinterpreted as follows, namely there is a diagram of the following shape. So we have such a cospan, W mapping to x and W mapping to x prime. and we're given a null homotopy eta, or a homotopy eta between the pullback of Q and the pullback of Q prime along the respective maps. So all of this happening in the space of forms on W. And okay, now I mean, you can imagine, I mean, it's easy to see that these two definitions agree, but if you think geometrically, it's super obvious, right? If you have a cobordism with two endpoints, you can just also say it's a cobordism from the disjoint union of the two endpoints to the empty set, right? By just viewing it sort of from some other side. And the very same thing is what we do here as well. So this picture we had before saying that x plus x prime admits a Lagrangian means the sum is null cobordant. And now we just say, well, equivalently, x and x prime are cobordant. Okay, and of course, this is subject to a non-degeneracy condition, which is satisfied, and which is very similar to that diagram that I indicated earlier. So in this situation, we have W mapping to x prime and x. In each case, we have an equivalence to the respective duals, dual of x and dual of x prime. Now these terms in turn map to the dual of omega by just dualizing these two maps.
Markus, sorry, can you repeat that? So what does this cobordism thing have to do with Lagrangians?
The statement is that, okay, yes, I can repeat this. So here the statement was that I want to say that two elements are related if their sum is metabolic, i.e. admits a Lagrangian. Okay?
Yes, I agree. Yeah.
Good. So admitting a Lagrangian, I want to convince you something like having a null cobordism. And instead of explaining that, I just tell you that this observation is supposed to say that admitting as having an object lying in the middle, which we think of the cobordism between x and x prime. Are you still with me?
Yes.
Okay, right. So W is the cobordism between x and x prime, which witnesses that there is some admits a Lagrangian. So in other words, W is also just the Lagrangian of the sum. Sorry.
But W needs a Q to be a Lagrangian, right? It needs a...
Well, no. The condition of a Lagrangian was a homotopy from f upper star Q to 0. Yeah. So if you imagine Q is 0, then this term is 0, and really we have a null homotopy of that term. So what I'm writing here is literally specializes to a Lagrangian if x or x prime is 0.
Thank you.
You're welcome. Right, okay, so such that some non-degeneracy condition is satisfied, and this non-degenerate condition is exactly that this canonical diagram you can write down as a pullback diagram. Okay, so in other words, what we want to construct is a space whose points are Poincare objects, and where two Poincare objects are related if there exists such a span between them with this relation. So let me call this for now a cobordism between W and between x and x prime. Right, so this will also be much more thoroughly explained in Jonathan's first lecture, where he defines cobordism categories, like the cobordism category associated to a Poincare infinity category in more detail. So please check out that video also. This will be very complementary to what I do here. Okay, so I have a couple of more minutes, so let me go through the following construction roughly. Namely, we fix a Poincare infinity category, and we want to define for each n a new Poincare infinity category, and I want to directly tell you that these are supposed to assemble into a simplicial object. So think of this n as the value of a functor on delta n, on delta. So we want to construct a new Poincare infinity category for each n equipped with simplicial base maps. And the way we do this is the following construction, namely we look at functors from the opposite of the poset of non-empty faces of delta n. Okay, so this is a typical add construction that has been used many times in the construction of Bordism spectra and L spectra. But okay, so tau n is just the poset of non-empty faces of delta n. You can look at functors with values in C, and we have to specify some quadratic functor, some Poincare structure on this category, and it's given by, okay, so this category with an op here, you can pull the op inside, you can apply copper pointwise, and then take a limit at the end. It's some formula you can concretely write down. that is not super relevant for the moment. But let me dwell on two examples briefly. So firstly, copper 0 is of course just C and copper, right? The non-empty phase pole set of delta 0 just consists of delta 0 itself, and nothing fancy happens. And row 1 has objects given as follows. What is the phase pole set of delta 1? Non-empty phases, this category looks like this, right? It's sort of the phases which are the two endpoints, and then the full phase with the two inclusions we have. Okay, so contrariant functors on that category give shapes of that sort, precisely the shapes that we've seen here that describe x and x prime being equivalent. And now, what is the quadratic functor? If you unravel this construction I did, well, what you do is you apply copper to each of these terms. What you obtain is this kind of diagram, and what you then take is the limit of this diagram. Okay, so in that case, it's just the pullback. And what is a point in the pullback? Well, it's exactly a point here equipped with a homotopy between their respective images in copper of W. So I want to say that again, if you've checked out Jonathan's lecture, what he wrote is Qn, that has to do with Q1, that has to do with the fact that there's also going to be a Qn category, and there's these row n categories that I wrote down, and they happen to coincide for n equals to 1, but not for the higher n's. But so you will recognize this construction from Jonathan's lecture. And it's a fact that the Poincare objects of this row 1 category are precisely Lagrangians in x plus x prime with respect to q plus q minus prime. So those are things that we would like to call cobordisms between xq and x prime q prime. Okay, so that's two, right? We wanted to say we observed that the L group is the quotient by an equivalence relation on the monoid of Poincare objects. The relation we can describe in terms of certain diagrams with a non-degeneracy condition, and then we realize then we can write those itself as the Poincare objects in some associated infinity category, which is this category row 1 of cobordisms between objects x and x prime. Okay, and so from here, let me say maybe just a bit more. The proposition that I don't want to prove, but I mean, you can imagine all these things are very canonically. I mean, all constructions were sort of functorially in terms of delta n and c copper at just limits flying around and everything. So the statement is that these assemble into a functor from delta op times cut infinity p. So this is an infinity category of Poincare infinity categories that we haven't described yet, but which I'm happy to explain more about in the coffee break later, which sends n and c copper to this category rho n of c copper. And in addition, that's something that I will explain then in the beginning of the next lecture, is that all the simplicial phase maps VI are what are called split Poincare Vernier projections, which is something, a very nice feature they have. And so what I want to finish with is the definition of the L spaces as the geometric realization of the simplicial space that we obtain by sending n to the set or the space of Poincare objects of this category rho n c copper. Okay, so that's supposed to be the definition of this L space. We look at the simplicial, the simplicial collection of categories rho n, c copper. To each of them, we apply the Poincare space functor, and then we let n vary, obtain a simplicial space, and take the geometric realization of the simplicial space. So let me finish really, I'm sorry, Thomas, give me 1 minute, with two little comments. Namely, firstly is that the space of Poincare objects of a Poincare infinity category, in fact, is an E-infinity space canonically. And one way you can justify this is by saying that, in fact, this functor is co-represented by some particular Poincare infinity category that also appeared in Jonathan's talk. And this category of Poincare infinity categories itself is pre-additive. So any mapping space will be canonically in infinity space. But of course, the operation of adding two things is just given by direct sum of Poincare objects. So it's nothing fancy. But what you see is that because all these Poincare spaces are E-infinity spaces, and the E-infinity spaces in spaces are closed under the formation of geometric realizations, this L-theory space is also an E-infinity space. And now I will in fact finish by only showing you this exercise, which says that, well, we can maybe not yet quite understand all homotopy groups, but you can already show that the pi0, so the group of connected components in this L-theory space I've constructed, is the L group that we've already done. So in other words, we will have already seen that L of C copper is a group-like E-infinity space, hence the connected spectrum. And a good exercise to do is that you can ask about what happens if I replace this space of Poincare objects just with the space of all forms. And it's a good exercise to at least informally convince yourself that this geometric realization is contractible. We'll make use of this in the beginning of next lecture. Okay, so I will stop the lecture at this point and we'll continue tomorrow. Thanks.
Okay, thank you very much. Yeah, so thank you, Markus, for this nice talk. At this point, I only want to allow one or two real quick questions. And for later questions, for more questions, I will refer to the forum that we have. And also right now, in 5 minutes, we'll continue. I mean, everyone can grab a coffee and then we'll have an informal discussion session here where everyone can ask Markus or some of the other authors. Jonathan is also here. More questions about that. But first of all, are there real quick questions here?
Notation question. So you wrote Pn rho n, and then to the right you wrote Pn of C.
Yes, that is correct, but both things are fine. So so
yeah,
that's why I added this is true for all CQ, in particular for rho n CQ.
Maybe can you remind me what the capital Pn notation meant?
Oh yes, that was this. Yes, of course. Sorry, that is this space of Poincare objects.
Oh, okay.
And here, so it's just the sub collection of all components in the space of all forms. So pairs x, q, where the associated map from x to the dual is an equivalent.
And you saw, I guess, if you take rho n, then that is again.
Yes,
you can
so,
apply this, I guess.
right. I meant to say that we define a new object, rho n of CQ, in Poincare infinity categories.
Ah, right. Okay, it's all there. I see.
Under the category, some emission structure, and then yeah, to it you can apply the Poincare space. And then I tried to explain that for rho 1, the Poincare objects are exactly these objects witnessing an equivalence between x and x prime, equivalence in the sense of giving rise to the same element in the L group that I've defined earlier.
All right, thanks for catching me up.
You're welcome.
Okay, further questions? Well, okay, so if this is not the case, then before we thank Markus again, let me say that we will make the slides of Markus as well as the presentation of Jonathan available on the homepage. So go there, you'll find the link in the description on the homepage or below the video. Also, again, let me say, please go to the forum if you have any questions. I mean, any sort of question, really. It's supposed to be useful for everyone. So if you don't understand something, probably a lot of other people will have the same problem. And then finally, we will now have a coffee session where we can ask informal questions or discussions to Markus, Jonathan, or many of the other authors of this project. Okay, but before that, let's thank the speaker again.